Okay. Hello. So let me move these slides. Okay. So quick show of hands. How many people have used the Uber app before? Okay. I'm not talking to a zombie audience. That's good. Okay. So if you're not staying at this hotel tonight, I would suggest that you use an Uber after the reception tonight. Stay safe. So here I'm going to focus on basically how Spark is used by the marketplace data team at Uber. I'm going to focus on real-time data processing and analytics, even though the forecasting team also uses Spark. Okay, so I should first probably explain what marketplace data is. So marketplace data refers to our geotemporal data, which is processed from an event stream. So in this case, geotemporal means it has a geospatial, geographical component and a time. And this data is used internally both for our services that need to know the state of our system, and it's also used to power some of our internal dashboards and business metrics. So if this was just some very easy, simple transactional data, we could probably store it in a relational database, and I wouldn't be here. But it gets a little more complicated because you get events, you have windowing, you have complex event processing, you have all sorts of reasons that we might want to use Spark. So in this case, when you use Uber, there is a rider app and there's a partner app. So there are two sides to the coin. And each one of these communicates with a backend service, which publishes events to Kafka. So let's say as a rider, you click a button, request a trip. That triggers an event, and that then matches you with a partner. And again, that also triggers an event. So these events, basically, when they get triggered, they change the state of the app. So there are two pickups in this example, followed by two drop-offs. So the vehicle in this situation was en route and then on trip. And it's a little complicated because there were two passengers. So the same windowing that we're doing applies to two riders and not just one rider. So with this kind of information, we can answer some simple questions, and we can use, obviously the reason I'm talking about this now is we can use Spark for this. We can answer questions like how many non-en route, non-on-trip cars are in London right now. We can ask questions about the historical driving times, the traffic in New York's financial district at certain days of the week. We can also ask questions about how many requests from a rider result in a trip, and if that conversion rate, just like an ad conversion, if that conversion rate is low, why is that the case? We also have more complicated questions like how many drivers cancel a request more than 3 times in a row within a 10-minute window. And we might want to know this information because it could indicate there's something wrong with our matching. And we want to know about that quickly because it could indicate a failure. So to solve this, we use complex event processing, and we provide like a SQL abstraction, and we can trigger events. So in this case, when that situation happens, a chat message is printed. We also want to do geospatial aggregation, and we might want to answer our question and get a value for the San Francisco Bay Area. We might want a value for the city of Oakland, for a particular neighborhood, or for BART train stations. So there are many solutions to pre-aggregating geographical coordinates. And the most well-known, I assume some of you have heard of geohashing, where you basically have a grid of the world, and you basically subdivide those cells in the grid into more grids, and each one of those grids has an identifier. So we don't use geohashes because they have some issues. Like one of those issues is that at the North Pole versus at the equator, the size of each grid is going to be different. It's the same issue that you have with a Mercator projection. So we use hexagons. They have some nice properties. They're kind of like geohashes. You can index them. They render nicely. You can aggregate them and cluster them. The distance between the center of a tile and the surrounding, hexagons is the same. You don't have this situation of diagonal squares. With hexagons, we have the same advantages of geohashes, and we can use them for density calculations. So then that brings us to where does Spark fit in? So I guess in an ideal world, what we would want, right, is the Spark's mission, might be to democratize data, and we want to do that too, right? We want to enable both our internal services and our data scientists to use the same service and to just empower them as much as possible to use Spark for that. So the reality, obviously, is never as easy. Otherwise, we wouldn't have jobs. So services, they want reliability. They want consistent performance. They care about P99. So they care about minimizing the worst case response time. On the other hand, data scientists, they want flexibility. They want features. And so when they want features, that allows them to break things. It allows them to issue bad queries. So for example, their query might lack a partition column filter. It might perform self-joins. It might have a very bad user-defined function. One common example of something that a data scientist might do, which is not intuitive at first, is they'll write a query and they'll do a dot cache at the end of it, and then they'll write another query which uses that cache thing, and they'll never use the rest of the data that was cached. So you've basically ruined the query optimization. I mean, you've materialized this intermediate step that you didn't need to. Also, Spark isn't a database. So if your data doesn't fit in memory, it's not indexed, your performance is not going to be as great. If you're storing a lot of states, the RDDs are immutable, so you want to checkpoint that DAG to disk so you don't have to keep track of it. But we're getting there. I mean, Spark 2.0 kind of unifies batch and streaming, and I think, of course, despite these limitations, it's an amazing tool. So again, I want to just explain the difference between interactive users and services. So interactive users, they care about features, they care about large time, they care about batch, they care about using these high latency systems. That's okay for them as long as they get the data they need. Whereas services, they care about availability, they care about smaller data, they care about quick, low latency responses. I have a quote here from a software engineer. This not necessarily at Uber. They said data scientists don't know how to code. Basically, you see this kind of conflict between data scientists and software engineers. Other challenges are, how do you get data scientists to easily discover what data sources they need? It's easy to isolate CPU and memory, but disk space, disk I/O, network I/O are kind of more complicated because your network I/O is not just dependent on your local machine, it's also dependent on the network switch. And again, I talked about bad queries, which whenever you allow flexibility, you also allow bad queries. It's a trade-off. So this is kind of our design at Uber. We have a lot of backend services that are written in Python, Node.js, Java, or Go. So these communicate with the app indirectly or directly. And then they publish events to Kafka. And those events that are published to Kafka eventually find their way either into S3, into Parquet, and HDFS, and Hive, or to Elasticsearch via a Samza streaming job. You can think of Samza kind of like a lightweight Spark streaming. And if data is missing from Elasticsearch, we backfill it from Parquet and HDFS. And we use Spark here to enable us not only to do the backfilling, but we also expose Spark to data scientists through Jupyter Notebook. And I'm going to get a little bit into the trade-offs that come with doing that. So we try to tell data scientists, and of course services, exclusively use this, to use our query service. So it's a Java service that validates queries and then issues it to Elasticsearch if it's validated and it's seen to not do much harm. And we get fairly predictable responses. I mean, not like a relational database, but obviously faster than a Spark query that's reading data from disk that's not cached in memory. So we have that, and that works well for those hexagons that I was talking about, pre-aggregated things. But sometimes data scientists want something more complicated. So for example, they might want to take latitude, longitude points and identify the airport that it's located in. Or they might want to do some more complicated queries that involve event times that we don't index. So for that, we enable them to use PySpark with Mesos. We're using dynamic allocation. I'll get a little bit into why we use dynamic allocation for coarse-grained mode. And in this sense, Jupyter, which, by the way, how many people have used Jupyter Notebook? Okay. Cool. So we use Jupyter Notebook kind of to unify the query service API and the PySpark API. So why Jupyter? Why not Apache Zeppelin or Databricks? So for everyone, there's obviously going to be a trade-off. And definitely, I think Databricks is probably the most refined, easiest solution with Spark. And I'm not saying that because I'm here. I'm saying that because generally the cloud product just works. So we use Jupyter, though, because of, when I say ease of use, I'm talking about the ease of use of data scientists who are familiar with it. Extensibility, I'm referring to, there are lots of libraries for Jupyter. There's a lot of documentation for it. We've written extensions and libraries for it. You can inject JavaScript, custom CSS, and we use that for visualization and data discovery. And we use the Python libraries to basically evaluate each cell and say whether that cell can be executed or not based on some criteria. It might be as simple as just a regex that says if you're including this in your cell, don't run that cell. It's bad. So this is a little bit about the diagram of how Jupyter, multi-user Jupyter works. This is an open source project. I'm not taking credit for it. So Jupyter, when a user basically accesses Jupyter, they go through Jupyter Hub, which is a multi-user Jupyter proxy. And that spins up a single user server, which then starts a single Python process for each notebook, running which they call a kernel. And we build a Python virtual end for each one of these kernels. So we manage these requirements.txt files with pipcompile. And inside these kernels, we capture the C-level standard out, standard error messages so that we can get the Spark driver, progress bar, log metrics, rewrite the cell execution if we need to. So in this example, as I kind of showed, the kernel then can communicate with Spark, or it can, through HAProxy, communicate with our other HTTP services. So I'm assuming most of you probably are familiar with how PySpark kind of works. Basically, you have a bunch of Python workers, and those Python workers, in our case, we deploy virtual envs for them so that they have the same environment as the driver. And then on the Mesos side, we use, again, dynamic allocation. This is just a very standard, how Mesos works. You have a elected master, you have zookeeper, quorum, so at least a majority of the masters need to be up, and each executor, each Mesos agent, as they're called now, then runs a number of Spark executors. So again, I'm going to quickly go through this because I assume most people already know this. So in Mesos, you have frameworks which are like applications that consist of two components. They consist of a scheduler, which talks to the Mesos master, accepts resources, and an executor, which launches tasks. And those tasks, in this case, are Spark executors. On the other side, we have a master and agent in the Mesos cluster. The master keeps track of all these resources in memory. One is elected. The agent runs on each cluster node. and it communicates with the master. So when a resource offer is made, basically the application has an option whether to accept or reject the offer. And in this way, you get a lot of flexibility. So resources, again, one of the issues that we had with Mesos was that isolation can be kind of difficult when you get beyond CPU and memory. So for example, disk I/O, or for example, network I/O. There are some bandwidth limits, but there's no way to kind of like split up the network I/O and say 50% to this, 50% to this. So there are some limitations that in a multi-tenant cluster you have to deal with that make things more complicated. So here's an example of when we put this all together, we're running a job through the notebook with PySpark. I'm using this example here because there's a reputation that Python is very slow, which is true, except when you use C extensions, you can get the performance a lot better, as the previous speaker, Wes McKinley, was talking about. So in this example, we're using Shapely and Artree. These are Python packages, the standard Python libraries. They both wrap libgeos, a C library, which is also used by PostGIS, and libspatialindex, which is not used by PostGIS, but is for an Artree index. And so you can kind of see here we're using the, I don't know if the text is big enough, but basically we're using Spark to send that index to all of the nodes. And that index basically is all of the airports, their polygons, and Artree index of them. And so then we're going through each record and saying, well, is this point in one of these airports? If so, identify which airport it is in. So basically with Spark, very quickly, without even having an index, of course this is a very simple example, but very quickly in a minute we can just run many months of records and just find out which airports they were in. And we don't have to even touch Scala, which is amazing, or good and bad. So the workflow kind of that we're trying to suggest to data scientists and getting them to use is, they use the notebook to explore the raw data and process it, and they use these libraries that we've written for curating their using curated queries, commonly used functions for geotemporal visualization. So what I mean by that is, how many people have used leaflet.js? Okay. So Leaflet is the thing that lets you basically create a slippery map, let's say like a Google map, and you can just put some data on it. You can plot a choropleth, which is just color-coded based on a value. And we kind of we take this a step further. We add a time slider to it so you can sort of see a certain metric, what was the value at a different time. And you can query whatever metric you want with Spark, so you have a lot of flexibility to make up your own metrics and visualize it within the notebook. And then eventually the goal is to get this code deployed. So in our case, we had some workarounds that we had to do. So I'm going to just mention them a little briefly. So by default, if you use Mesos today, you're probably going to use the Mesos coarse grain mode in 161. In our case, we wanted to go a step further. The issue with coarse grain mode is you're hogging resources. And when you have a data scientist using the notebook and hogging an enormous amount of resources, just sitting idle the whole day, you can't run a cluster like that. It would be very expensive. So we're using dynamic allocation, which, thanks to the work that the committers have done, works pretty well. But we had to backport 13 commits from the master branch. So these would be in Spark 2.0 to fix dynamic allocation and launch multiple executors per node. We deploy Python virtual enums to the Spark executors. The reason I mention this as a workaround is that in Java, it's very easy to kind of deploy a jar and just package all of your dependencies in the jar. Whereas with Python, that's not very easy, especially if you have C extensions. Another workaround that we do is we stitch Parquet files together. And the reason we do that is so Spark keeps track of each partition on the driver side. I think it calls this like Hadoop FS relation or some object. And so this is my understanding. So if the Parquet files are too small, you have a lot of Spark partitions, and the driver will end up running out of memory. So we have to actually stitch the partition files together to allow Spark to use them. There are a few other issues that we had. One was limits aren't exactly always pushed down. Spark will still scan all the partitions. So that's kind of not intuitive for a data scientist when they run Spark SQL and they say select X, limit 100, and it ends up scanning the full partition column of data. Another issue is there's no support for Mesos checkpoints yet. So that means if you restart the Mesos agent, say if you're upgrading the Mesos cluster, it ends up killing all your Spark executors. And there's no support yet for Mesos oversubscription, which basically allows, like with other frameworks, allows you to steal idle but allocated resources. So with that said, there's a talk by my colleague. You should go to it tomorrow. And there's some other resources, and that's it.